Hey everyone, welcome back to Math 111. This is Scott. Let's get started. What we're going to do now is put a little brief addendum on top of section 3.3. So this is an addendum to section 3.3, and the topic that we are going to cover, which is not covered in your book, but which we are still covering we're covering anyway, is concavity. All right. So in section 3.3, we talked about functions having intervals of increase, intervals of decrease. We also discussed such things as rates of change and so on. Now, what happens if the rate of change is itself changing? So concavity is the result of changes in the rate of change of a function. In other words, changes in the slope. All right, so let's think about what this means. So whenever we say changes, we mean as it goes from left to right. So there are two flavors of this. Either the rate of change can be going up as we move from left to right, or it can be going down as we go from left to right. So concave up. So this refers to the situation where the slope increases as we move from left to right. Now, increasing, that can mean one of two things. That can mean either it's positive and it gets more positive, or it can mean that it's negative and it gets less negative. So that either means more and more positive, which then would look like this. So it's got an upward slope and an upward slope and a steeper and steeper upward slope, or less and less negative. Which means that it is going down, but it's tapering. It's getting a little bit more level. So these are the two flavors of concave up, and notice in both cases, if you were to draw little eyes on top of the graph would appear to be smiling. So concave up is a feature that where the graph appears to be smiling, versus concave down, which is the opposite situation. So the slope decreases. As we move from left to right. So this can mean either more and more negative, which would look like something that was falling at an accelerating rate, or less and less positive is the other way to decrease. And of course, here we're talking about the slope. So the graph itself can be positive, it can be negative, it can be above or below the x-axis. The important thing is the slope. Now, again, if you draw little eyes on top of it, the mood of these graphs is sad. And this leads to an old nursery rhyme. Concave up, like a cup. Concave down, like a frown. Now, if a graph has any straight line segments in it, then its rate of change is not actually changing, it's actually just holding steady. So note graphs. Graphs that contain straight line segments have no concavity. Over those intervals. And the reason is that the slope is not actually changing, it's holding steady. So slope isn't changing, it's constant. Now, when it comes to concavity, we'll ask similar questions to what we asked in the case of increase and decrease, namely to find intervals where the function has where the function is concave up versus concave down. So the goal here would be to find the intervals over which a graph is concave up or concave down. And the key here is to look for where the mood changes, where it goes from smiling to frowning. So the key, I should say. So the key to accomplishing this is look for the x values at which the mood, quote unquote, changes from a smile to a frown, or vice versa. If there's one thing human beings are basically made to do, it's read facial expressions. And so let's just tap into that. We'll hack our own brains and use them to help us to determine when functions are concave up or concave down. So let's try an example. Identify the intervals on which the following are concave up and on which they are concave down. Alright, so let's take a look at a little graph like this. So let's say it goes up, goes down, goes up again, like so. Now, important numbers for us in this might be right here, which is 0. You can tell by the presence of the y-axis. And perhaps we will also think of these numbers as being important, so let's say that is -2, this is +2. Now we're not even going to concern ourselves with the specific values of the y coordinates here, because whenever we talk about intervals, we are always talking about intervals of x values, not intervals of y values. So let's think about this. Let's look at the mood here. So clearly this function is sad, 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 still sad, still sad, still sad, not as sad though. But by now, the function appears to be happy. So it looks pretty sad throughout the whole negative side of things. It looks pretty happy starting about 0, starting about x equals 0. So right about there. So it appears to be concave down, like a frown, until 0. So negative infinity to 0, and whenever it comes to the concavity, we'll always leave the intermediate point unclaimed. So we'll always use the parentheses to indicate that we are not interested in including that. And then concave up. Oops. Concave up. Oops. Concave up. And that'll be from 0 to infinity. So notice it went increasing, decreasing, increasing, but that wasn't really the question. The question was, where is it concave up? Where is it concave down? Now, let's have a look at a graph with just some straight lines like that. Straight line like that. Now here, it's holding steady, so if you look at its mood, and don't get distracted by what happens later, but if you just look at its mood in the short term here, it's very stoic. It's like a Vulcan. Same thing here, very, very stoic. Sitting there, taking it all in, taking it all in. Same here, same here, same here. It has no concavity anywhere. No concavity. And the reason is it's always, its rate of change, its slope that is always constant. It's constant, it's undefined right here, and then it's constant again. So it's constantly positive, not defined, and then negative. Alright, and then lastly, let's take something like this. So let's go one swoop, one swoop, one swoop, and let's say that it ends at open circles. Let's call this -3, 0, -1.5, +1.5, positive 3, 4.5, and then here we're at positive 6. And again, we're not even going to bother writing in what the x or what the y values are, because questions of intervals of this, intervals of that, are always questions that pertain to the x values, intervals of x values. So these are purely x values that we are interested in. Now, asking ourselves about the mood, looks pretty happy. It's very happy. 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 Hard to say, but certainly by now, it's sad. Sad, 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 happy, happy. And so clearly, somewhere in between, its mood changes, and you just kind of eyeball where that must be, and it looks like it's right in between the peaks. So, we can say concave up, concave up, so there are two intervals in which is concave up. One is negative 3 to 0, and again, because the circle is open, that means the negative 3 is certainly not included. Borderline points are always a little bit iffy no matter what. And here, we are not going to say that that point is either concave up or concave down, because it's an ambiguous little turning point. So there's that interval. And then there is the next interval, which goes from apparently 3 to 6, but not inclusively. And don't use a union in between these, because this is not a specific interval. These are two different intervals. We're just listing them. This is a list of intervals. It shouldn't be considered as a single set. And then concave down. That's going to be the intermediate space, which is from 0 to 3, but again, not inclusively. 0 and 3 are turning points, as you'll learn in a later math class. Those are called inflection points, points where the concavity changes. But to learn more about concavity, you have to keep on the mathematical train until you get to calculus. When you take calculus, that's Math 251, you'll learn not only what concavity looks like, which is the very vague description we've just given, just kind of a smiley face or a frowny face, which happens as the slope gets more and more positive, less and less negative, etc. But you'll be able to put a specific number on it. It'll be what's called the second derivative. To learn more, take the exciting class Calculus 1. Available wherever math classes are sold. Alright, well that will just about do it here for the addendum to section 3.3. I'll see you for the next episode of Math 111. Bye!